So yeah, thank you very much. I'm presenting this joint work between all the collaborators. You can see the screen, two of them in this very room, Mario and Hao Chung. Ligao was also here until yesterday, and also my supervisor, Andreas Winter. So we've named this work bypassing joint typicality in network quantum Shannon theory, but this work truly emerges from, let's see if this works. Yeah, from two other independent projects that were conducted by these two different groups, and they had very different goals, but well, maybe not very different, but different goals, and happened to stumble upon the same problem and solved it in a very similar manner. So this fundamental similarity between both of the works made us yeah, coordinate and present this joint submission to QIP that I'm presenting right now. The first work was was aiming to generalize decoupling to a multipartite version. The second one to generalize convex splitting to a multipartite version. And both of them try to apply the results to some quantum information tests that I will explain in time. These two works together, this joint effort yield an extensive number of results. Some of them they are pretty technical. So I wanted to concentrate the efforts of this talk on understanding first of all what is joint typicality and why we want to bypass it. Then I will move on to explain how we perform this bypass, which is a very simple trick. And finally, we will see how this applies to these two quantum primitives, to decoupling and convex splitting. And finally, I will just present the applications. So that's the plan. Let's start with talking about joint typicality. So in a classical setting, we usually want a multipartite probability distribution to be typical in several of its marginals at the same time. And we create these jointly typical sets that have some amazing properties that we will use for analyzing encoders, analyzing decoders, for creating tasks of pinnacle importance such as source coding, right, in classical settings. But the problem is that when we move to quantum, we do not have an analog in the desired generality. So if we try to define something that looks like quantum state joint typicality, we do not find a definition that gives us the same amazing properties that we use in classical. And this is a problem, and it's due to the main difference, right, between the quantum states and probability distribution. So if you want to understand this maybe more intuitively without luring you into a lot of technicalities, you can think about the quantum marginal problem, which is the difficulty of inferring quantum information of a general state when you only possess a partial part of the state. And this, as a matter of fact, any kind of transmutation between partial quantum information to the information of other partial systems, other marginals, and the information, especially of the general state, is difficult. Even in some kinds, it is impossible to do. So this big marginal quantum marginal problem reduces to this joint typicality problem, and also to simultaneous smoothing, which is something quite similar that I will explain in just a few slides. I really think that the best way to understand all this is just go straight ahead and try to solve one of these quantum primitives, and we will stumble upon the problem, and then we will just try to bypass it with this trick that I want to present. So without further delay, let's start talking about decoupling, which is a task where you have some correlation in the input state row between the systems A and E, and you want to do some local manipulations on the system A such that the output looks something uncorrelated from if and kind of uniform. So that's the idea, the main objective of decoupling. And mathematically, we could write this something like, like this thing you can see the screen. So the expected difference between what we have, this manipulation of the input state, and this uniform and uncorrelated thing has to be something small. That's the main thing we want to achieve. And it was analyzed, this single user scenario was analyzed by Dupuy, Verta, Wurtzleg, and Rena. And in this paper, one-shot decoupling, and they saw that this can be achieved, this decoupling can be achieved with a process that involves a random unitary chosen from a two design and a fixed CPTP map. And they actually found a bound for this expression here that that depends on a term on this quantum entropy here, that if you're not used to this kind of entropy notation, you can understand it just as a term an object that quantifies the amount of correlation that this input state has, and another term that accounts for the, let's say, amount of decoupling power that our map has, right? So this would be an upper bound for this expression here that we want to make small. And the thing now is, can we try to generalize this to a multipartite setting? So if we now create k aliases, A1 to AK, and we apply these random unitaries locally on each one of them, and after that, a general CPTP map on all of them, we want, again, the output of this thing to be something that is uniform. This starts to look a bit more messy because it's multipartite quantum info, so everything is going to look messy. But yeah, something uniform and uncorrelated from the system E. And again, we want to bound this expression here, which again looks very messy, but it's the exact same thing as before. We have the quantum state where we have applied the random unitaries, and after that the CPTP map, and we are calculating the expected difference between this thing, our manipulation, and this thing that we are aiming to. So the this uniform and uncorrelated thing. Now, what we would expect when we sort out this object, this trace distance here, is that we find terms again that account for the decoupling power, the decoupling power of this map here, but also terms that account for the correlations on the input state. And notice that we would expect that we have a term accounting for each one of the marginals and if, so for the correlations of each one of the marginals and if, but not only each one and if, but also each pair, each three kind of, so any kind of marginal of Alice, we want to account somehow the amount of correlation that it has with if. So we will have this whole set of objects, this whole set of quantum entropies, and we expect one for each possible marginal, right? And this is when simultaneous smoothing comes into play and we stumble upon the problem. Let's just first see what the problem is, what is smoothing and what simultaneous smoothing. Smoothing is just an optimizing problem where we just want to compute a certain quantum entropy in the best state around an epsilon ball. So the best state around an epsilon ball around this our input state, right? So we do this to bypass any kind of atypical behavior that our input state could have. Maybe it has an eigenvalue that is zero. Maybe it has some kind of marginal purity, and this sometimes can make quantum entropies go rogue. So we just we just smooth this so we can optimize these the error rates that we are calculating. And the problem comes with simultaneous smoothing, which is a conjecture, the simultaneous smoothing conjecture, that says that if you find for a general multipartite state this smoothing state, this rho prime that maximizes some kind of, or minimizes, that optimizes some kind of entropy, then a reduced entropy will have to be optimized by a marginal of this input quantum, so of this rho prime that we have found. And this is maybe some kind of stretch, but it's a conjecture that was made long ago and no one has proved. Maybe it's easier to understand with an example. Imagine that we want to smooth these two entropies here. Simultaneous smoothing would mean that we find this rho prime that optimizes the first entropy, and automatically this rho prime, so the partial trace of this rho prime, should be the one that optimizes the second entropy here. And this is what I said, that this kind of a stretch, it was conjecture, but it hasn't been proved. So we want to avoid this, the use of this simultaneous smoothing, and instead use independent smoothing, which is just finding some rho prime 1 and rho prime 2 that optimize independently each possible entropy, without hoping for any relation, any spatial relation between rho prime 1 and rho prime 2. And now if we return to the slide before, we see that all this set of entropies that we are expecting when sorting out this big partial trace here will always depend on this first term here. And now if we just put side to side this big expression here, so with this with the example before, we see that this looks like the first scenario here. Just hang on with me for a second and you will see, well, we will try now to bypass this thing, and with the trick, which is the main trick of this talk, the main issue. But you will see when we see where we started and where we end, you will see the differences between this simultaneous thing and the independent thing that we come up to. So the main trick is super easy. We just have to define this map, which is just a subtraction between the random unitary we use for decoupling, and this completely depolarizing channel. And we also define this, let's say, reduced CPTP map, which is just our initial CPTP map, but applied only on a marginal part of our input state. And now we just have to notice that there is this telescoping trick, so that we can write this expression here, this expression here, the one be above, just as this one, this sum of over all the possible marginals that you can see here. Maybe it's not super clear how this happens, but if you think about this minus sign that you have here, and you think about the distributive law that we will have to apply on each term of the sum here, we'll have a whole lot of terms, but a lot of them, like half of them, will be negative, and they will cancel out each other, I promise, and you will end up with this thing above. So just after this telescoping trick, we can just apply the definition of this partial map, and finally the triangular inequality, and we end up with something that looks like that. Now, if we check the differences between what we have before and what we have now we can treat each of these terms independently. So each of these terms will produce an entropy, the entropy we were expecting. So the whole sum, so this set here will produce the entropies for the marginal it is accounting for, and we have a sum over all these marginals, so we can treat independently, as if it was the single user scenario, each one of these terms in the sum. So now we will be able to smooth independently everything. Before we had to do everything over the same state, now we can do we can work just with the marginals. This is the main idea, and I don't want to get further in technicalities, but I guess that you can see more or less how this works. And with this very simple trick, we can bypass joint typicality and get straight to the results in decoupling, which are just, well, yeah, this error bound that we wanted to calculate looks like a sum over all these marginals that we have seen in the trick. And again, some exponential of these objects, of these quantum entropies that we were expecting. And we also have some constants that that appear in the calculations, but intuitively this can be understood easily if you think that stronger correlations on this input state will mean smaller entropies and therefore a greater overall bound, and this means that we will commit more error in decoupling, which makes sense, right? That stronger correlation will make decoupling more difficult, and also if the map is closer to 1, so doing virtually nothing to the input state also results in a smaller entropy, so in poorer decoupling, which also makes a whole lot of sense. But the takeaway idea is that with that very simple trick, we can generalize the single user version of decoupling to a multipartite version, so to this multipartite quantum version, right? And we can use exactly the same for another quantum primitive, which is convex splitting, where we want to approximate the product state be a convex combination of correlated states. So given this correlated state rho and some other state tau and m, we can define this omega in a very clear way, in a very clever way. And well, yeah. So picture now in omega 1 would be the state that has a correlation between A1 and B. Omega 2 will be the one that has a correlation between A2 and B, and so on and so forth. And what we want to do now is to make the convex combination of this. This is summing everything up, dividing it by m, and the thing that we get when we combine everything, so when we do the convex combination, we want it to be similar to the product state. So to this thing you can see on the screen. And again, mathematically, this can be written as this trace system between what we have and what we want, right? And this would, well, yeah, be the definition of the error. And the thing now is, what is the actual relation between the integer, so the amount of copies we have of the initial tau, and this error that we commit. And this was sorted out recently by some of the collaborators. And what we want to do in this project actually is to generalize this again to a multipartite version of convex splitting. So the idea would be the same. We will have a tripartite state now, and we will have two indices and two integers. So again, this omega 1,1 will be the state that has a correlation between A1, B1, and E. Omega 1,2 will be the state that has a correlation between E, A1, and B2, and so on and so forth. And we have to do the same for A2, for A3, and for all the A's to up to AM. So when we have all these correlated states that we have defined, we just combine them, we do the convex combination, we divide, we sum them up, we divide it by M1, M2. And again, when we do this, this convex combination, we want this to be similar to the product state, which is the thing you can see on the screen. Now, if we focus again on this expression here, this is the bipartite case. It's not yet like the full multipartite version, but in this bipartite case, we already see, well, or we can understand that there, at some moments when trying to sort out, as it happens before in the coupling, when trying to sort out this trace distance here, we do not get the objects that we want because, again, of joint typicality of smoothing problems, simultaneous smoothing issues. So again, we just have to use the telescoping trick to get something that transforms this thing here in something that looks like a sum over all the marginals of a manipulation of our input state. And if we do this, and this can be done, we can again treat each marginal independently, similarly to the single user scenario, and we get the possibility of generalizing this to a multipartite version. The results would be the ones you will see in the screen. Again, we have to define this convex combination of correlated states, which again looks very messy because this is now the fully general case, right? And again, we will find that something that is a sum of over all the marginals of an exponential of the generalized again information. Again, if you're not used to this kind of notation, you can just interpret it intuitively by saying that this object here will be smaller if the state is closer to a product, and therefore we will have a smaller error in multipartite convex splitting when we have a state closer to product, which makes a whole lot of sense, right? Now, the takeaway idea here, and the takeaway, the reason why I have explained this to primitives is that this telescoping trick actually is very useful to pass from, thank you, from the single user scenarios to multipartite versions. So just let me advertise for another time this takeaway idea, which would be if you are you ever got stuck with these simultaneous smoothing problems or joint typicality problems, if you're trying to generalize something and you are not getting the rain informations that you would hope you would be getting, I really I really how do you say that? Well, I would want you to try this brand new telescopic trick that we have created, because as you can see, it worked in these two primitives, and we are hoping that it will work also. I mean, it's a very general thing, so we are hoping that it will work also for more general scenarios. And to show you that it is not for very technical quantum information things, I'll show you the amount of results that we have gotten just by generalizing these two primitives into multipartite versions, which is this table here. On the left-hand side, you can see the set of applications that we have worked out. In the middle, you can see the previous state of the art before our paper, so the things that were known about the rates of these tasks. And on the right, you can see the results that we get, the applications that we get with our new results, which is, well, yeah, it's always a full characterization, or almost always a full characterization of this task in the IID setting, in one-shot settings, and even in some cases on the compound settings. I also would like to show you the references for this previous state of the art, which are those here. So if anyone is interested, you can take a picture. And with this, yeah, I think that's all I wanted to say. Thank you very much for listening. And yeah, and I will leave you with this slide, which is more beautiful. Thank you.
Thank you very much. The floor is open for questions. Please approach the microphone if you have any question.
So could you describe what exactly is the telescoping trick in this most general form?
Sure.
Just abstractly? Or...
Sure. Let me go a lot back. So it is just, well, a telescoping trick is just when you express some some expression as a sum of a whole lot of terms that will at some point cancel each other out and go back to the first expression, right? So the thing is, sorry, there are too many animations. Now, so the thing is that the telescopic trick appears and can be seen and can be, if you work it out in the two user scenarios, it's quite easy to see. It's the difference between this sum here. So just focus on this sum here and this thing here only and this other thing here. So if you apply this definition inside this thing here and you sum everything up, and then you do like the how do you call that, the distribution law and so on and so forth, when you multiply all these things here, you will end up exactly here. And that is the main thing, and this just happens. So if you want to apply this, you just have to find a clever way to express, imagine that you have some expression that looks something like that. You just have to try to express it in some way, like these differences between what you have and some kind of completely depolarizing channel, which is why we get these identities here, right? And if you achieve this, then you can probably write everything up as this sum, and then with this easy definition and the triangular inequality, you end up being able to use this everything independently instead of simultaneously. So that is, yeah.
Thanks for the talk. So in the classical setting, states are just distributions, and you have all the typicality bounds that you can have in the context that you showed in the last slide in the table. So you consider the quantum states here, which maybe we can also think of as represented by quasi-probability distributions. Do you think there is a point in thinking about typicality bounds for quasi-probability distributions more generally?
Yeah, sure, but the notions, I mean, in the previous slide, there was some kind of sense of the quantum typicality, right? But those are usually when you apply classical probability distributions to quantum states, or you have some special quantum state like pure states, which are in the end classical distributions. So the thing is, in some cases, you can define this some kind of quantum joint typicality, especially when there's a thing called quantum entropy typicality, something like that, which are typicalities defined on entropy quantities, right? But if you want to use joint typicality in the same sense that is used in classical information theory, so classical multipartite information theory, you cannot really find a definition for quantum states that have all the properties you would desire.
Oh, makes sense. Thanks.
Sure. If anyone is interested in some applications, I have some extra slides and I can bore you for another hour. So
if there are no more questions, let's thank the speaker again.